Welcome to the Deep Dive. Today we're tackling, well, a classic puzzle in physics. Why don't atoms just fall apart?
Right. I mean, think about it. The early picture was like a mini solar system, right? Electrons orbiting a nucleus.
Yeah, like tiny planets. But classical physics had a huge issue with that picture.
A massive issue. Those orbiting electrons, they're accelerating. And accelerating charges should radiate energy continuously.
Meaning they'd lose energy, spiral inwards.
And crash straight into the nucleus. Boom. The atom should be unstable, gone in a fraction of a second.
But they're not. Atoms are incredibly stable. They make up, well, everything. So how did they survive that classical death sentence? Let's unpack this.
And this is where Niels Bohr enters the picture back in 1913. He basically looked at the rules of classical physics and said, maybe these rules just don't apply here.
A pretty bold move.
Incredibly bold. He proposed that electrons don't gradually slide down that energy spiral. Instead, they jump.
Jump.
Yeah, jump between specific allowed energy states. Only certain orbits, certain energy levels were permitted. Nothing in between.
So energy isn't continuous down there. It comes in chunks.
Exactly. That was the birth of quantization. Energy, motion itself, comes in these discrete packets. It was revolutionary.
And that's what we're diving into today, Bohr's breakthrough.
Right. His insights that saved the atom, conceptually speaking. And then we'll look at how a more modern framework, motion theory, reframes all this.
Motion theory.
Yeah, it sees quantization not just as a weird atomic rule, but as something much more fundamental, like a universal principle, almost like, well, motion's natural compression algorithm.
A compression algorithm, like for digital files.
Sort of, yeah. Nature, finding the most efficient, stable ways for motion to exist, and discarding the unstable stuff. Our mission today is really to explore how motion itself might shape reality.
Okay, so back to the core problem Bohr faced. Classical view. Continuous motion, electrons radiate, atoms collapse. A huge puzzle.
A complete dead end for classical mechanics, really. If it were true, matter shouldn't exist as we know it.
So Bohr just threw out continuity.
Essentially, yes, at that level. His radical assumption. Electrons live only in specific stationary states. And crucially, while they're in one of these states, they don't radiate energy.
So they're stable there.
Exactly. They only emit or absorb energy, like light, when they jump from one allowed state to another.
So classical view, smooth ramp. Bohr's view, staircase.
Perfect analogy.
Yeah.
You can be on step 1 or step 2, but not hovering halfway between. It was completely alien to classical thinking.
You mentioned motion theory gives context here. How does it see things like space and time?
Right. So motion theory provides a different foundational view. It sees reality itself not as objects sitting in space, but as structured motion. Patterns of movement synchronizing under constraints.
Okay, motion first.
Motion first. And space isn't an empty box. It's more like unresolved background change. A sea of potential motion before stable patterns emerge.
And time?
Time is seen as a comparison. The sync rate between different moving systems. How fast one pattern changes relative to another. Not some universal clock ticking away.
Interesting. What about energy and mass?
Energy is basically tension within motion. Think of a wound spring, potential movement. And mass. That's the inertia of rhythm, the resistance to changing a pattern of motion.
That inertia of rhythm, I like that.
Yeah, and bringing it back to Bohr, quantization, in this view, is that natural compression algorithm we talked about. Motion finding its most stable, efficient forms.
So Bohr makes these wild assumptions, breaking classical rules. But did it work? Did it predict anything real?
Oh, absolutely. That's the amazing part. He took the simplest atom, hydrogen, just one proton and one electron.
Oh, yeah.
And he proposed a specific rule. The electron's angular momentum, sort of its orbital spin quantity, could only be integer multiples of a specific value, h2 phi.
Right.
Planck's constant divided by 2 pi.
A very specific mathematical condition.
Very specific. And the incredible thing, when you applied that rule, the allowed energy levels it predicted perfectly matched the actual colors, the spectral lines that scientists observed when hydrogen gas was excited.
Wow. So the math, even though it seemed arbitrary, matched reality exactly.
Exactly. It was a stunning success. It showed quantization wasn't just a guess. It was somehow built into the fabric of the atom, even if classical physics couldn't explain why.
But motion theory does offer a why, right?
Yeah.
Here's where it gets really interesting.
Yes. From the motion theory perspective, Bohr's rule isn't just a magical decree. It's about survival.
Survival of motion.
Precisely.
Yeah.
Why don't electrons crash? because only certain kinds of motion loops can actually persist. They have to close cleanly.
Close cleanly. What does that mean?
Think of the electron not just as a particle, but having a wave-like nature too. Imagine that waves traveling around the nucleus.
Okay.
If that wave doesn't perfectly meet itself in phase after one orbit, it interferes with itself destructively.
Like ripples canceling each other out.
Exactly. It bleeds energy, it becomes unstable, it fades away. It just can't sustain itself.
Ah, but if it does close cleanly.
Then it reinforces itself.
Right.
Every cycle, the wave pattern overlays perfectly, strengthening itself like a standing wave.
Like a guitar string vibrating at just the right frequency. It resonates.
Perfectly put. Those self-reinforcing loops are what Bohr called stationary states. Motion theory calls them coherence locks.
Coherence locks. I like that term too.
They're patterns of motion that are inherently stable because they reinforce themselves. They lock in.
So quantization isn't a mystery rule. It's motion's way of ensuring stability. A survival filter.
That's the idea. Nature automatically selects for the motion patterns that cohere, that endure. The messy, self-canceling ones just don't last.
So Bohr absolutely nailed the existence of quantization. He saw that the atomic world wasn't continuous. That was the huge leap.
A monumental leap. He fundamentally changed the game, even though his specific model had limitations.
Right, you mentioned it didn't work so well for bigger atoms.
Correct. It struggled with atoms having more than one electron and couldn't explain things like electron spin, which came later.
So other theories came along.
Yes, wave mechanics from Schrödinger and matrix mechanics from Heisenberg around 1925-1926. They provided a much more complete mathematical description.
But Bohr's core idea stuck.
Absolutely. The fundamental insight that not all motion is allowed, that nature picks only the loops that reinforce, that became a cornerstone of quantum mechanics, it endured.
And motion theory says this isn't just about atoms.
Far from it. That's what's really fascinating. Motion theory suggests this principle of coherence, of stable loops, applies across incredible scales.
Like where else?
Well, we've talked about atomic orbitals, those electron clouds. They're precisely these stable, closed loops of the electron's wave function.
Okay.
Then you go into the nucleus, the magic numbers that make certain nuclei extra stable. Motion theory sees those as synchronized loops of protons and neutrons coherence clusters.
Inside the nucleus itself. Wow.
Yeah, and even bigger. Think about planetary resonances in our solar system. Why do some planets have orbital periods that are simple ratios of each other?
Like Jupiter and Saturn.
Exactly. Those are orbital loops locking into stable harmonics. It prevents chaos, keeps the system stable over billions of years. Self-reinforcing gravitational patterns.
So, wait. You're saying the same basic logic, motion finding stable, repeating patterns, applies from electrons to nuclei all the way up to planets?
That's the suggestion. The fundamental logic of stability through coherence seems to be scale invariant. It's about motion finding ways to persist by reinforcing itself.
That's genuinely mind-bending. It connects the incredibly small to the cosmically large through one principle.
And Bohr wasn't just about the physics equations. He also thought deeply about the philosophical implications. He came up with this concept of complementarity.
Complementarity? What's that about?
It's the idea that something can have seemingly contradictory properties like being both a wave and a particle, and both descriptions can be true just depending on how you look or measure.
So an electron isn't either a wave or a particle, it's somehow both.
Depending on the context, yes. Bohr felt nature couldn't be squeezed into just one single picture. You needed multiple complementary views to grasp the whole.
How does motion theory see complementarity?
It frames it as, well, different ways of probing the coherence of motion. Motion simply expresses different aspects depending on your interaction with it.
Can you give an example?
Sure. If you measure motion in transit, focusing on its rhythm and propagation, like light traveling, you see its wave nature.
Okay, the continuous flow.
But if you measure its interaction, the loop edges, like detecting where a photon hits a screen, you see its discrete quantum nature, a particle-like event.
So the measurement itself determines which aspect you see.
In a way, yes. It highlights different facets of the underlying coherent motion, which makes you wonder, what other aspects of reality are we missing because we only look from certain angles?
That's a deep question. You know, Bohr's Institute in Copenhagen sounds like it was an incredible place. The House of Quantum Motion.
Oh, absolutely legendary. You had almost anyone in early quantum physics passing through there. Heisenberg, Pauli, Dirac, Fermi, Gamow.
Wow. Imagine the discussions, the debates.
Intense, certainly. All grappling with this new reality that motion itself was quantized, restricted. The very nature of reality was up for grabs.
And of course, the famous Bohr-Einstein debates happen there, right?
Yes, the intellectual sparring between the two giants. Einstein famously saying, God does not play dice, expressing his discomfort with the randomness and probabilities inherent in quantum mechanics.
And Bohr's reply?
Stop telling God what to do.
Hmm.
Classic Bohr. For Einstein, quantization felt incomplete, like there had to be hidden deterministic rules underneath.
But Bohr felt quantization was the reality.
Pretty much. He accepted it as a fundamental feature of nature. And motion theory, interestingly, kind of bridges this.
How so?
It suggests quantization isn't arbitrary, like Einstein feared, nor is it just a weird brute fact, as Bohr perhaps accepted. Instead, it's the natural outcome of motion-seeking coherence. It's how motion must behave to be stable, not random chance, not hidden variables, but the inherent consequence of self-reinforcing dynamics.
Let's circle back to hydrogen then. Bohr's first big win. You said we should reframe how we see it.
Yes. Think beyond just a simple orbit. We observe those specific spectral lines, those exact colors of light.
Right. Empirical fact.
Bohr's rule, angular momentum is quantized, explain those lines mathematically.
Okay.
But the motion theory view gives the physical reason. Only electron loops with integer self-phase can persist. The electron's wave has to fit perfectly around the nucleus, an integer number of wavelengths.
Circumference equals n times wavelength. Like that guitar string again.
Exactly. It's literally a closed wave resonance.
Yeah.
Any wave that doesn't fit perfectly just fizzles out. Only the resonant frequencies, the coherent loops, survive.
So hydrogen isn't just a particle orbiting, it's like a tiny motion drum resonating.
That's a great way to put it. The electron's rhythm is locked to the proton's anchor, creating a stable, resonant system. It's dynamic harmony, not just static structure.
And that simple atom is the universe whispering.
Whispering its fundamental law. Stability equals coherence. Persistence comes from self-reinforcement. It's shown right there in the simplest atom.
Now, Bohr mostly focused on atoms. But you said motion theory takes this quantization idea much further.
Right. Bohr saw it as primarily an atomic thing. Motion theory argues it's a universal principle. Quantization, or at least coherence, is everywhere.
Give us the grand tour then. Where else?
Okay, quick rundown. We have electrons and atoms, orbitals as closed loops. We have atomic nuclei, magic numbers as nucleon coherence clusters. We have molecules, quantized vibrational modes, stable oscillation loops.
We mentioned planets and orbital resonances.
Yep, stable harmonic loops in gravity, then look bigger. Fractal clustering of galaxies in the cosmos, strange quasar alignments over vast distances, the very structure of spiral galaxies. These all hint at large-scale coherence, preferred patterns.
Wow. So coherence patterns might structure the entire universe.
Motion theory even suggests framing the very origin, not as a Big Bang explosion, but as a great motion event. The emergence of the first stable, self-reinforcing loop of motion from the primordial background change.
The first coherence lock?
Exactly. And from that initial seed of stable motion, quantization cascaded upwards, allowing complexity to build atoms, stars, galaxies. Maybe even life itself is a highly complex form of coherent motion.
Okay, so reflecting on Bohr's legacy now, with a century of hindsight and ideas like motion theory, what did Bohr perhaps miss, or what can we add now?
Well, obviously, he couldn't have known everything. Concepts like zero-point motion, the idea that there's inherent motion even at absolute zero, that wasn't part of his picture. Motion theory sees this as the fundamental background hum from which coherent loops emerge.
What else?
The idea of coherence gradients. Maybe quantization isn't always a sharp oh-no-af thing. Perhaps coherence fades gradually with scale or complexity, but the tendency towards stable patterns persists.
Interesting. Not just sharp steps, but maybe fuzzy boundaries sometimes.
Possibly. And a really big one. Understanding information as motion. Seeing memory or even prediction not as static data, but as stored, repeatable loops of coherent activity like patterns in neural networks, perhaps.
So a thought is a motion loop.
That's a way to conceptualize it within this framework, yes. A persistent, recallable pattern of motion. So motion theory isn't replacing Bohr, it's extending his core insight. Quantization isn't some arbitrary atomic quirk.
It's the universal grammar of motion.
Exactly. The fundamental way motion organizes itself to create stability and structure everywhere.
What an incredible journey from a collapsing classical atom to a universe built on rhythm and coherence. Bohr's genius was his courage, wasn't it? To just stop forcing the old rules.
Absolutely. He accepted that the atom played by different rules, that motion itself imposed limits. Those allowed states in hydrogen weren't arbitrary. They were simply the only ways the electron's motion could survive, the only loops that closed.
He found stability in the pattern, not the particle itself.
And while his model was, yeah, a brilliant first sketch, later filled in by Schrödinger's waves and Dirac symmetries, the heartbeat of his idea is still there. The universe selects, it prunes away unstable motion. It favors coherence.
Bohr cracked open the atom and found rhythm.
And motion theory suggests that rhythm just scales up, echoing through molecules, planets, galaxies, the entire cosmos.
So Bohr's atom wasn't the end of classical physics after all. In a way, it was the beginning of seeing reality as fundamentally based on motion.
Motion first reality.
Which leaves us with a thought to ponder. If stability truly equals coherence, if persistence comes from loops closing and reinforcing themselves, where else in your world do you see this? In your daily routines, maybe? In successful relationships? Even in ecosystems?
Right.
Where do you see motion loops closing, creating something stable, enduring, and, well, resonant?